got to go to the White House. He said it's one sort of expectation when he's going to.
Yeah.
Well, thank you very much.
White House is really tough. It's just
It's time to begin our forum today. We are very fortunate to have a distinguished panel that's going to address the question of talent in engineering and the importance of talent. You know, I'll introduce the panel briefly, shortly. It's a very extraordinary talented panel that comes from entirely different perspectives to this problem. And the range of perspective is going to be very important because clearly, if we're talking about talent in engineering, there's a wide range of perspective that tracks the wide range of engineering. You know, in fact, is there a problem in talent for engineering? And can you evaluate talent without knowing what the expectation is of the engineer to begin with? And you know, if there is a problem for talent in engineering, how serious is this problem? You know, is it just a Band-Aid required to fix it? Is it structural change that's required to fix it? Is it something that the engineering profession itself should take on to fix it? And is there this standard for talent that, in fact, a nation must achieve in order to ensure its security and prosperity? Can you talk in terms of these terms or not? And of course, what are the steps the U.S. could take to ensure that it has the talent needed for its prosperity and security in the future? So the talent question is a very big question. Now let me introduce the panelists to you. I'll introduce the panelists in alphabetical order, so just to not show any particular bias at all. And on this end, it seems to be on the, I guess it is alphabetical, maybe they're already on. Anyway, Dave Baggett is on my right-hand side. He heads Arcode Corporation, which was founded in 2008. Arcode's first product is called Inky. Is revolutionizing email user experience and making email smarter, simpler, and safer. Prior to founding Arcode, Dave Baggett joined a video game company called Naughty Dog in 1994, where he co-developed Crash Bandicoot series for Sony PlayStation. The Crash games were a worldwide bestseller that redefined the state-of-the-art, leading Sony to adopt Crash as its mascot. Mr. Baggett then founded ITA Software with two other MIT AI lab graduates. The company developed the first new airfare pricing and shopping software in decades and licensed technology to most U.S. and international airlines. Its technology powers Orbitz, Kayak, Humpmonk, whatever that is, and many other travel industry websites. Well, Hipmunk, I guess.
Hipmunk.
Google actually purchased this software for a lot of money in 2011. So Dave Baggett holds a bachelor's and master's degrees in computer science and linguistics, actually, also from Maryland and MIT. Sitting next to him is Bill Banholzer. I think you're retired now, Bill, haven't you?
End of the year.
Pardon?
End of the year.
Oh, end of the year. Good. Okay, not yet retired. He is the executive vice president and leading Dow Chemical Company's venture capital, new business development, and licensing activities, and is also Dow's chief technology officer. He chairs the company's Innovation and New Business Development Committee, which oversees investments in new technologies and major business initiatives. Dr. Banholzer manages a portfolio of research programs at Dow with an annual budget of $1.7 billion, sets the company's vision for science and technology, and leads, in fact, the execution of that vision. Bill Banholzer earned his bachelor's degree in chemistry from Marquette University and master's and doctoral degrees in chemical engineering from the University of Illinois. He's a certified Six Sigma Master Black Belt. Next to him is Sir Alec Ambrose. He spent nearly 20 years of his career in research at IBM in USA. When he arrived back in Cambridge, he set up a nanofab lab to extend the technology of miniaturization to the atomic scale. He also developed his research on using electrons, X-rays, and on making microelectronic components. Lord Browers was elected to the Royal Society in 1986, to the Royal Academy of Engineering in 1985, and became a foreign associate of the U.S. National Academy of Engineering in 1994. In 1996, he became Vice Chancellor at Cambridge, a position he held until 2003. In 1998, he was knighted for his service to higher education, and in 2004, Her Majesty the Queen made him a life peer in recognition of his contributions to engineering and higher education. In 2012, he became chairman of the judging panel for the Queen Elizabeth Prize for Engineering, which was awarded by the Queen in 2013. Lord Browers received his first degree in physics from Melbourne University, and then he received a degree in electoral sciences from the University of Cambridge after arriving initially as a choral scholar. I guess he had to sing for his supper, and completed his PhD at Cambridge in 1965. Next on the list is John Montgomery, who is Director of Research at the U.S. Naval Research Laboratory, where he oversees research and development programs with expenditures of approximately $1.2 billion per year. During his career at NRL, he has been responsible for numerous systems developed and approved for operational use by the Navy and other services, and had great impact through the application of advanced technologies to solve unusual and severe operational deficiencies during world crises, most recently in Afghanistan, Iraq, and for Homeland Defense and in the Pacific Theater. Holder of numerous awards, Dr. Montgomery was elected to the National Academy of Engineering this year. He received his Bachelor of Science degree in Physics from North Texas State University, his master's degree in physics, and he received a PhD in physics from Catholic University. Dr. Subra Suresh became president of Carnegie Mellon University on July 1st of this year. Prior to that, he was director of the National Science Foundation, a position for which he was nominated by the president and unanimously confirmed by the Senate in 2010. As director of the $7 billion independent federal agency, he led the only government science agency charged with advancing all fields of fundamental science and engineering research and related education. From 2007 to 2010, he was Dean and Vannevar Bush Professor of Engineering at MIT. His research into properties of materials and discoveries of connections between cell properties and human diseases has shaped new fields in the fertile intersections of traditional disciplines. Subra Suresh has been elected to the U.S. National Academies of Science and Engineering, the American Academy of Arts and Sciences, and 7 international academies. In 2011, the President of India awarded him the Padma Shri, which is one of India's highest civilian honors for his contributions to science and technology. Dr. Suresh received his Bachelor of Technology degree from IIT Madras, his master's degree in Iowa State, and PhD from MIT. Marie Thursby is a Regents Professor and holds the Hal and John Smith Chair in Entrepreneurship at the Scheller College of Business at Georgia Tech. She has been a research associate of the National Bureau of Economic Research since 1987. In 2002, Dr. Thursby founded the nationally acclaimed program Technological Innovation, Generating Economic Returns, a unique educational collaboration between Georgia Tech and Emory that teams PhD students in engineering and science with MBA and JD students in experiential curriculum focused on the intersection of technological, legal, and business issues at the heart of innovation. She has published extensively on economics of innovation, with particular emphasis on the role of universities in innovation systems, multinational R&D decisions, and the role of contracts in effective technology transfer. Her current research focuses on incentive problems in biomedical translation research and in information sharing among competitive researchers. Dr. Thursby received her bachelor's degree in economics from Mount Holyoke College, her PhD in economics from the University of North Carolina at Chapel Hill. Now, our moderator today is Christine Romans. She is the host of Your Money, CNN's Saturday and Sunday business program. In addition, she reports on the economy, politics, and international business for CNN's morning shows. She received an Emmy Award in 2004 for her work on Exporting America, a Lou Dobbs technology investigation into the impact of globalization on U.S. workforce, and was part of the coverage team that earned CNN a George Foster Peabody Award for its Hurricane Katrina coverage. Ms. Romans is the author of 2 books, How to Speak Money and Smart is the New Rich. She's a graduate of Iowa State University. With that, Christine, the floor is yours, and I'm very much looking forward to the output of this panel. Thank you very much.
Start with Dr. Suresh.
Thank you, Christine. May I have the slides, please? First slide. It's a great pleasure to be part of this panel. Last time I spoke at the annual meeting in this room, the fire alarm went off in the middle of my talk. I hope it won't happen today. So I want to show just 5 slides on issues that I have been an observer to over the last few years, first in my role as director of the National Science Foundation, and currently from my vantage point as president of Carnegie Mellon University. Could I have the next slide, please? So there is a major shift taking place on a global stage with respect to talent. And there are many different ways to look at this, but from my vantage points, there are four major topics that I think will shape how talent is searched and recruited around the world. The first is investment in research and education, which creates the talent, and the shifting changes that are taking place on a global scale that will perhaps forever redefine how the talent is created. Secondly, the shifting demographics from around the world that will shape the hunt for talent for the decades to come. The third item is that we face many grand challenges, global challenges, and the National Academy of Engineering has articulated 14 grand challenges for the 21st century. Given the fact that global challenges invariably and inevitably need global solutions, that is going to define how we interact and how we recruit talent on a global stage. And the last item is that we live in a borderless knowledge enterprise where all the policies that create talent, either through funding or through human interactions, are local or national. But the output of that process has no borders. And that creates a whole set of questions for which, at this point, nobody clearly has articulated an answer. So at the end of these 4 or 5 slides, I will put up a set of questions. So let me start with investments on a global scale. So talent requires two things. We need the money to support the talent, and we need the people to do the work, people with talent. So this graph is the latest graph from Battelle, from a number of different sources. It talks about R&D investments on a global scale. So the most recent year for which we have data, which is 2012, the total R&D investment on the planet was $1.4 trillion US dollars, adjusted for purchasing power parity. On the x-axis, you have dollar investments into R&D. So R&D as a fraction of the GDP of a country. On the vertical axis, you have people investments into R&D, the number of scientists and engineers per million population. So both these axes are normalized with respect to the size of the country, either the economic size of the country or the population size of the country. You see 4 colors here. So you don't have to read any of the graphs. All the green circles are the Americas. The largest green circle in the middle is the United States. Then you have Canada just below that. And then way down below, you have Brazil. Those are the only 3 countries in the Americas that fit into this graph. All the others are too small to be on this graph. The size of the circle is related to the size of the investment. Larger the circle, larger the investment. The blue circles are all Asia. So you see Japan, South Korea, even small countries like Singapore, Australia. China and India are to the bottom, but China is moving up extremely fast. And China is becoming a larger and larger circle as well. All the orange circles are Europe, and you see the Scandinavian countries, and then Germany, Switzerland, Austria, etc. If you add up the areas of all the blue circles, all the green circles, and all the orange circles, they are roughly equal. In other words, 1/3 of the R&D investment in the world is in the US, 1/3 in Europe, and 1/3 in Asia. The Asian 1/3 is increasing very, very fast. And according to the National Science Board last year, for the first time in the history of science funding, the R&D investments of the top 10 Asian countries surpassed the US. That has never happened before. The 2 countries in red that are here are Israel and Russia. So Israel is farthest to the right in terms of R&D investment, and Finland is closest to the top in terms of both investments and people. Now let's go from dollar amounts to people. So let's look at the world. This is the most recent data that's available. In 2009, the number of college freshmen in all the colleges and universities in all the 50 states of the US combined, and added to that the number of college freshmen in all the universities and colleges in all the 27 countries of the European Union combined, and added to that the number of all the college freshmen in all the universities in Japan combined, that in 2009 equaled the number of college freshmen entering universities just in China. So the number 1 economy in the world, the number 3 economy in the world, number 4 economy in the world combined with respect to college entry equaled the number of college freshmen just in China. That's the input to college. Let's look at the output from college in 3 different parts of the world: Asia, EU, and United States. This is what Dan Moat mentioned yesterday in his speech at the induction ceremony. In Asia, 20% of all the college graduates are engineers. In EU, it's about 12%, but in the US, it's about 4%. And we've been getting worse and worse. We used to be about 7% just a couple of decades ago. Not only that, there is one other point. Last year, for which we have the data, only 1.4% of all the college graduates in the US were women engineers, for half the population. So this begs the question, if the US is so bad with respect to engineering domestic talent, how did we become the unquestioned innovation leader in the second half of the 20th century? There are many, many complex answers to this, and nobody has the right answer. But one of the contributing factors to the success of the US in the last half century is that the institutions, the processes, the mechanisms we had developed in addition to funding were such that we could pretty much get anybody we wanted from anywhere in the world to come here, work here, stay here, and become US citizens. So 25% of all the American Nobel laureates had their first degree abroad. 25% of all the members of the National Academy of Sciences had their first degree abroad. When I was Dean of Engineering at MIT, I knew the numbers just 3 years ago. 43% of all the MIT faculty members in engineering had their first degree abroad, 375 of them. So there is an economic argument to this talent attraction. If you look at the bill that's going through Congress, 100,000 highly talented people coming as immigrants, if that bill passes, look at the dollar value of this. It takes about $500,000 to educate a child from the time the child is born to the time the child reaches the age of 22 and graduates from college in the US. 100,000 people, $500,000 a pop. That's $50 billion in investment into US R&D enterprise by some other taxpayer in some other country. That's what we have benefited from for the last 60 years. I know, I was one of them, and many of you in the room are also in that boat. So let me just finish with my last slide, the borderless knowledge enterprise. What are the major questions? We can make all the policies we want in Washington for the input. The output has no borders, so the question is, who is in charge? Currently, nobody. And what are the questions here? Who will develop policies and practices that will ensure compliance for shared and collaborative global scientific enterprise? Who will organize, distribute, store scientific information and what we now call big data? And even more importantly, who will pay for it as we archive it and curate it across rapidly changing platforms? Who will create policies that will protect privacy, confidentiality, and intellectual property? There are organizations, but in this knowledge enterprise involving universities and funding agencies, who will do this? Who will develop validation technology for the educational enterprise that's massive and online? And who will make sure that it has the right quality on a global scale, not domestically? And last will be, how will institutions and individuals participate in an enterprise with open access to publication data, and who will pay for it, while addressing local and national needs? So we don't yet have the answers to this, but the good news is that some organizations are starting to think about it. 2 years ago, the major funding agencies from around the world, with blessing from the White House and the State Department, were gathered at the National Science Foundation, and we collectively formed an entity called the Global Research Council, which represents about 98% of science and engineering funding in the world. That group is starting to look at these issues, not only how we will coordinate, but how we will actually pay for it through taxpayer money from different countries. So this is going to be a critical part of the global talent enterprise. Thank you.
Thank you very much. Dr. Montgomery. Great, your job. Your turn. Dr.
All right, I'm John Montgomery from the Naval Research Laboratory here in the District of Columbia. And we're sort of a different corner of the world from academia and industry, being internal Department of Defense laboratory. So I want to touch on several things that, what the laboratory enterprise is, why we have these labs, what makes up the workforce in the laboratories, what are we going to need in the future, and more important to this discussion, how and where are we going to get them, which is a bit of a challenge that we see. So what do we have? What's the enterprise? Each military service has a corporate laboratory. There's the Army Research Laboratory and headquartered in Adelphi, the Naval Research Laboratory headquartered in D.C., and the Air Force Research Laboratory in Dayton, Ohio. In addition to that, each service has a number of engineering centers and centers for medical research. So when you look at it overall, there are actually over 200 sites with technical capabilities within the Department of Defense. And of course, you got to ask yourself, why do we have this enterprise? And the real reason for having that enterprise is because the military arts and requirements are highly technical. They're founded both in science and engineering, whether it's the basic science that led to GPS or to radar or sonar or any of the other tools of current military art. And so it's been the policy of the Department of Defense to support and use this resource. So why do you have them? You got to maintain national competency in areas that are important. You got to understand what's going on in the rest of the world to avoid surprise, to have scientists and engineers who are part of the world science and engineering communities who can go out there and harvest the knowledge that other people have paid for across the world and bring that knowledge and understanding back into the U.S. and to build upon what they've learned, and they in turn can build upon ours in a larger and truly a global enterprise today. That maintaining the tech base of the Department of Defense is critically important, as well as providing advice to senior leadership, to acquisition, and in many cases to programs which are operational in nature, where technological resources have to be harnessed quickly and brought to bear to deal with crises or military issues that are surfacing in various theaters across the world. An example might be the improvised explosive devices in Iraq and Afghanistan. So what makes up that workforce today? Well, there are 67 Department of Defense laboratories. In those laboratories are some 61,000 employees, 35,000 scientists and engineers, and the throughput of those laboratories financially is about $20 billion per year. If you look at the makeup of the workforce of that, there's 74% engineers and 26% scientists. And of those, 10% are PhDs, 27% have master's degrees. So that's sort of one end of the spectrum, and within that spectrum, there's considerable variability. So, for example, if you look at the Naval Research Laboratory, the Navy's corporate lab, we're 54% PhDs and about 24% in master's degrees. Overall, across all of the entirety of the Department of Defense, there's some 150,000 scientists and engineers. These just aren't in the laboratories. This is across DOD-wide. 47% of which are engineers and 35% are computer scientists, engineers, computer specialists. Overall, that represents about 2% of the national STEM workforce. Now, you'd think that 2% compared to the national workforce that may have some roughly 3 million of these folks in it, that the quantity of people out there available to us were practically infinite compared to the actual needs that you have. But it's really a matter of talent and capability and how we build the needs for the future. So it's not quite that simple. And one of the issues that constrains us is you need to be a United States citizen to work in these laboratories and centers, and you may need to have a security clearance. I'll touch on that a little bit later on. So what are we going to need in the future? Well, obviously, as you pointed out, that the world is changing. The intellectual centroid of scientific and technical activity in the world is moving eastward. We're becoming a smaller part of a larger whole. And as a consequence, that if we're going to harvest the knowledge worldwide for the Department of Defense and for the nation, that we need to be able to have more peer collaborators with scientists and engineers worldwide. That's critically important, that nobody is going to, in a country outside the U.S. or even within the U.S., want to collaborate with somebody that's not on the cutting edge of research in their particular field. It's just sort of like I have a sister-in-law who's a semi-pro tennis player, and there's absolutely no advantage to her improvement in skills by playing tennis with me. In fact, it's extraordinarily embarrassing, and she refuses to do that anymore. So that what we really ought to be doing right now, looking at the relatively small fraction of investment made in science and engineering, $1.4 trillion across the whole world. You know, isn't that what we increase our deficit by every year? Extraordinary. So we've got an increasingly technical world that's going to have increased demand for numbers, growing breadth of disciplines as new ones emerge, demanding more and broader and more diverse skills, that we're going to have to collaborate much more internationally. You know, that we have at NRL about 1,200 collaborations in colleges and universities, but only about 200 of those are within colleges and universities abroad in some 30-odd countries. We need to do more of that. In the future, we'll see more demand for math and computer skills, but also for engineers who know how to design and build and innovate, scientists and engineers with the scientists with the breadth of understanding to communicate and partner with engineers. But these aren't easy to get. You know, engineers, the curriculum is difficult. It's a densely packed curriculum. Other paths to good jobs are easier. You know, that I don't know what the average salary is of a scientist or engineer. In my organization, it's probably a little less than $100,000 a year. On the other hand, if I were tall enough to be a basketball player, I might be pulling down $3.5 million a year. So there's a sort of a sense of public value in scientists and engineers. I heard yesterday that the appreciation of engineers in the U.S. was 5 times that of congressmen. And so given that level of appreciation of 75%, you'd think everybody'd be wanting to do it because, frankly, in my 45 years in the business, I've never been bored for an instant, always been challenged. I can't imagine a better life that somebody could have. So how do we get them to invest more in that? Well, you know, people don't invest in what they don't value. They don't value what they don't understand, and they don't understand what hadn't been taught them or communicated with them. What we do is really pretty arcane to what the rest of the world does. I spend a lot of time talking to Department of Defense leadership, and it's amazing the lack of understanding of some of the basics of science and engineering. So very challenging proposition. A lot of entry-level jobs are moved offshore. So, you know, how are we going to get them? Well, got to have great work for them to do. That's why NRL survives, that it's on the great work. You got to have excellent facilities. That's declining in DOD. You got to have a lot more flexibility for people to do the science that they want to do and have the flexibility to build their own careers, shape their scientific interest and be rewarded for doing that. And of course, that would mean competitive pay. One of the things that we've been looking at in conjunction with the Office of Science and Technology Policy, the Department of Defense, Department of State, and Immigration and Naturalization Service is how could we provide a fast track to citizenship for those most highly qualified foreign graduates of our colleges and universities who might wish to remain permanently in the United States. I understand some 38% are electing to go back home these days. And so our proposal has been this. If they'll come to the lab, pass a background investigation that from a nation with which we have reasonably friendly relationship, when they come to work for the Naval Research Laboratory, they get U.S. citizenship on day one and a secret security clearance. And then perhaps on an opportunistic basis, we'd have a different opportunity to get to the best and the brightest, much of which is being funded indirectly through the Department of Defense, and get them to come to the laboratory. The most valuable tool for us has been the opportunity to bring people into the laboratory environment and do research, even at a very early stage in their education, with practicing, highly skilled scientists and engineers. So to that end, we bring in about 500 students every year from high school through college, even through the PhD, about 140 postdocs, and we embed them with our scientists and engineers and give them real work to do with real scientists. And after we've done this for several years, somebody might say wage psychological warfare on them, that at the end of that time, they often come to the laboratory. And I think that's a model that can be very useful. Nothing is more exciting than to be a young scientist or engineer in your educational process and get embedded with a large cadre of those folks who are really excited about what they do and give them tremendous challenges. And of course, the opportunity to participate in the world scientific and engineering community through conferences and collaborations, which right now in the Department of Defense are totally suspended. So, in summary, you know, that we got labs because military systems need to be state-of-the-art. We need world-class scientists to harvest and collaborate worldwide and to avoid surprise, bring home knowledge other people paid for. Science and technology is becoming vastly more global, and we need to be part of that global community integrally. So in order to do it, we need great work, good facilities, and competitive pay to attract and keep. Thank you.
Your point about the appreciation rate of Congress, I looked up these statistics this week. Root canals, head lice, and colonoscopies rank higher with appreciation than Congress at the moment. I really did look these up in the poll numbers just to try to bring it home. Next, the outlook from the UK, really another global outlook. Lord Alec Brower is here, and you're single-handedly trying to raise the stature of the profession in your home country. Tell us.
Well, I wouldn't say that, but I am here. I was born in India, brought up in Australia, and have lived equally in the UK and the USA, so I bring that perspective here, and I always enjoy joining in these discussions. One thing we share between the UK and the USA is that we love self-criticism and flagellation. And the US is always going down the drain, and everything's going wrong, but when I looked at Subra's little chart there, it didn't look that way to me. And looked at from Europe, I think you've got to remember that where the US still sits, quite dominant in high technology exercise. But of course it is changing dramatically. At our international breakfast this morning of the Foreign Associates that Venki hosted, it became singularly obvious that this academy is collaborating with countries all over the world now. Not only the emerging countries in the East, but there's also in South America and Brazil and places. The world's becoming immensely complicated. We have to look at everything from a global perspective. And if we want to compete, then there's no other way than to stay in the high technology end of the business in we Western countries. If you looked at that chart, you would find the UK not particularly well placed. We only spend 1.7% of our GDP on R&D, which is lower than almost any of the Western countries. We have issues there. We have issues with engineering. At the moment, however, I'm reasonably optimistic. The government realizes this at least and is taking several steps to try and improve the situation with respect to attracting engineers, to joining the global community of engineering. I'll spend the latter third of what I want to say talking about the Queen Elizabeth Prize for Engineering that Dan Moat mentioned, and Dan was one of our judges for that and did a splendid job, and the Academy's been very supportive there. But let me give you a few specifics just to give you an idea of where a small country like the UK is sitting. We too see that we're going to have a situation where demand for engineering, perhaps more broadly for science, engineering and technology graduates, is going to far exceed our supply. By 2020, it's been estimated, and the Royal Academy of Engineering's looked at this in some detail, we're going to need some 830,000 SET professionals by 2020. However, we are only going to produce at best about 89,000 a year. We need 100,000, and that's a gross number. We then have to realize that particularly in the UK, a lot of those students are overseas students, and increasingly they're leaving afterwards, and in any case, we've made a mess of our visa policies, and we're not encouraging them to stay. And I think the US has had similar issues. Some have been resolved, but we mustn't close our doors to the international market. Second, we lose about 28% of our engineers and SET graduates to other professions that aren't based on SET. And I mean, I'm not just saying they've gone to the financial world. If they've gone to the financial world and they're considering SET issues, then they would still be in SET jobs. So we need to up our output by about 50%. Which is going to be quite a challenge, and I don't know quite how we're going to do that. We're going to have a shortfall, we estimate, of 360,000 graduates by 2020. Not the 25 million that Dan mentioned that China's going to be out in the world seeking, but that may make our problem even worse. And I think we probably share this issue with other smaller countries. The Royal Academy of Engineering's been looking at this in great detail. There is good news. Similar to a lot of countries, and I think, Marie, you're going to talk about this too perhaps, but we in fact in the UK see a significant salary premium for engineers. Engineers earn about 15–16% more when they graduate than other graduates, some of them in sciences even. However, our engineering profession is very fair, very sort of socialist, and the spread has never been high enough for me. We lose people to the city of London because they will pay a good graduate twice what they will pay an average graduate. Our engineering companies still tend to be conservative, and an absolutely top graduate may get 10 or 20% more than an average. And that worries me because we need the cleverest, the very best people into engineering, and we've got to learn that there are big differentials. And I think maybe, David, you're going to talk about this, but outstanding engineers, people with outstanding SET skills can change the entire complex of a company. Just a few, so one mustn't look at just the averages. But we have maintained in the UK a fixed, what we call flat cash, science, engineering and technology budget from government, which has been quite an achievement. What that means is it's not being inflated, but at least it's not being cut like everything else. And you've got to realize the UK economy, we went through a double-dip recession, almost a triple-dip recession, so things have not been very good. We also have a problem across the spectrum. If we look at all the engineers we need, then our top four universities are performing very well, and they're getting very well qualified students. Their grades are very high. But roughly the 50% of the engineers that we need go to our newer universities, what we call post-92 universities. There are about 63 of those, and there are about 46 pre-92 universities. There, the grades fall off very rapidly, and they're having a terrible job attracting people with adequate skills, especially mathematical skills. In fact, the House of Lords Select Committee, which I'm a member of, just wrote a report on higher education in STEM subjects, and our strongest point is we've just got to look at maths education. It has slipped and slipped and slipped. And we're not going to create modern engineers if they do not have mathematical competence. We have that overall problem in challenging young people to become engineers, and some of the recent data are appalling. Engineering UK carried out a survey of 12 to 16-year-olds in schools and found that less than 20% knew what a modern engineer did. Only 38% of them even considered it as a respectable career. So there's immense ignorance out there. People have no idea what's going on. But as I say, the good news is that a lot of that has been recognized. And one thing that we've achieved was to establish this Queen Elizabeth Prize for Engineering, which is a new international prize. It joins the Draper Prize and the Finnish Millennium Prize. One thing we did with this prize, and I'm very pleased to see the Draper Prize is modifying its name as well, we were determined that this prize would be a prize for engineering, using that word, not using applied science or technology or anything, but engineering. Try to rub it into people that engineers are not just changing the oil in motor cars and fixing your washing machine, which tends to be. Strangely, in Britain, with its very rich language, we don't use the language as even Americans do. I mean, the word mechanic has basically disappeared, and serviceman isn't used, and linesman isn't used. It's always the engineers who are out there putting up the electric wires and fixing the car. And so I remember being quite depressed when I went back to the UK in '84, and I turned on the television, and the first thing I saw was an unleaded gas was arriving. And there were 3 of the Queen's Rolls Royces there, and the engineers were adjusting the carburetors so they could use. And I said, oh my God, nothing has changed. Recently, it is changing, and the government realizes this very well, because when the proposal for this international prize came along, and we engineers have been looking at this for years, all the institutions, could we perhaps take on that task of really producing a large international prize with the caliber of Nobel Prizes, but for engineering? But of course that takes money, and we were not terribly good at raising that money. In fact, the support came when an Oxford graduate in philosophy, politics and economics called David Cameron decided as Prime Minister that he might be able to do something about this, and he really took on this task with the other 3 political leaders who all jumped forward. And an MP, Oliver Letwin, was charged to go out and raise money, and within weeks he had raised $40 million, about 26 million pounds, to fund this prize. So it's an independent, it's not a government, it's not a British prize, it's set up, it's being the administration for it sits inside the Royal Academy of Engineering, but it's not really a Royal Academy of Engineering prize, it's an international prize in and of itself. It's overseen by a board of trustees. John Brown, ex-BP, chairs this, but there's the presidents of the Royal Society and the Royal Academy of Engineering and some others. I chaired the international panel of judges. We had 15 judges. They come from all over the world. Dan Moat was one of them. Chuck Vest was invaluable in helping us discuss this prize in the beginning and how we would get it in place. We've got judges from Germany, from Saudi Arabia, from the US, quite a lot of judges from the US, from the UK, from China, from India, from Japan. They come from all over the world, and we tried to mix the disciplines. 5 of our judges are women, but we have expertise all the way from directed evolution to agricultural engineering. The prize was announced about almost 2 years ago now. The winners were announced in March this year, and the Queen, who has thrown her entire support behind this, quite remarkably, of course, her husband, the Duke of Edinburgh, has been very important to engineering in the UK. He was really the leading person who, in the founding of the Royal Academy of Engineering some 35, 36 years ago. So they've really, the royal family, thrown their support behind this in a big way. And the Queen presented the trophies and cheques in Buckingham Palace on June the 25th, an event which was attended by the Prime Minister, by the leader, all the political leaders. It got very high profile. The prize was awarded to Bob Kahn, Vin Cerf, Louis Pouzin, Mark Andreessen, and Tim Berners-Lee for their contributions to the creation of the Internet and the World Wide Web. One thing that we judges were charged for doing was to look for an accomplishment that had already been of great benefit to mankind. Distinguish ourselves somewhat from Nobel Prizes, always looking for new science and other things. We want something where engineers have changed the world for the better in a big way. And when we started looking, we looked at everything from airliners to control theory to plastics to directed evolution, as people, engineers have to do. We cover the waterfront, a fascinating task. But 2 things that were different, really. One was that we wanted the prize already to have been of great benefit. Another was that we asked everybody who were even candidates for the prize, before we made the decision as to who would win the prize, that they had to commit to proselytizing for engineering subsequent to winning the prize. And that's been very successful. These judges have been going around schools all over the world, and the judges in their own countries also pushing engineering. So it's a great international enterprise to lift the profile of engineering, to make the world realize that it has all these challenges that really can only be resolved by engineers. These problems are exceedingly difficult, and we need very talented people to do it. So that's all I have to say. I'm optimistic in many ways that the world is realizing the importance and the responsibility that we engineers carry, and I hope that we're moving towards being successful in attracting the best.
And remind us how many engineers are in the House of Lords and the House of Commons?
Well, there's one research engineer. It's myself. There are quite a lot of industrialists who have been in engineering.
I think you could argue more engineers at the top levels of government, maybe we wouldn't be shut down in this country. I don't know if you agree with me, but we could use some more critical thinking, perhaps. Let's move on to Dr. Marie Thursby, the only economist on the panel. Yay, a woman after my own heart, running the numbers and the economics. Go ahead.
So I represent the dismal science. The other thing that economists are known for is saying on the one hand this and on the other hand that. so I'm going to live up to my profession. I'm really going to make one overall point and then two subpoints. And one is, if you look at the growth in GDP in the U.S. in the last 60 years, there's no doubt it's mostly attributable to technological change and innovation. Engineers are clearly an important driver there. But innovation is really the adoption of inventions. It's not just invention itself. So the only way an economy is going to capitalize on that is to have a system that really integrates the engineering, allows individuals and other economic units to profit from that. And I would maintain that that has happened in the U.S. So that's my overall point that I hope you will get from this. But on the way to getting there, I want to say a little bit about the supply of U.S. engineers. When we focus on the 4.4% of undergraduate degrees in engineering, it sounds pretty dismal. And a number of people have talked for years about declining interest in engineering among undergraduates. So I want to give you some numbers on that and ask the question, is it declining? And if so, why? And some factors to watch in that. And then I want to come back to, really that first part is going to be looking at numbers, okay? If you look at the demographics of the U.S. and China, there's no way just on numbers, even if we were to increase the number of engineers we produce 100%, that we're going to match the numbers. And so I would maintain that the competitive advantage of engineering in the U.S. Is really a broader mission, and this goes back to a quote I have there, making the connections. That's not my statement. It comes from Joe Bordogna. It was in a National Academy publication in the 90s, that really engineers had to be able to not only be technically fit, but they were the people who really had to make connections. And I want to come back to the role of universities in that. Okay. Looking at the numbers, if you look at U.S. engineering degrees awarded since 2003, there's actually been an increase. There's been a dramatic increase, okay, at all levels. There's been a 40% increase in undergraduate degrees awarded, 24% at the master's, and a 71% increase at the PhD level. The PhD level is the one I know the most about personally, and it's one that's quite important in terms of research that firms are conducting as well as governments. So let me give you a slightly different map of the production, and that's just looking at PhD production. And this goes from, these numbers were compiled by a friend of mine who actually wrote a wonderful book on economics of science, and it just as well applies to engineering. And it's looking at PhD production from 1920 to 2011. I don't know how easily you can see it, but the top two lines are engineering and biological sciences. The PhD degrees awarded is more than triple that for those professions than any of the others in science and engineering. So that doesn't sound quite so dismal, okay? Well, that's the supply of engineers. Suppose we look at the demand for engineers, and we've been talking about needing engineers, but if you actually look at the job market, and again, I'm going to focus on the PhD market because that's the one I know the best, and after all, if I wanted to get the statistics on the other degrees, I couldn't do it because the National Science Foundation's website is shut down. So we're stuck with what I know. Okay, if you look at this, it looks more or less level in terms of definite commitments means offers for jobs or postdoctoral positions, jobs in industry, government, or academia. It looks more or less level, but if you look at it very carefully, since 2001, if you were to put a trend line there, there's a slight decline in the commitments for those graduates, okay, across all of the sciences and engineering. And so what's happened at the PhD level, and this is something I'm very passionate about, I think it's a real problem reflecting some degree of disequilibrium in the job market, and economists don't like disequilibrium. Essentially, it used to be the case that the life sciences were where you saw postdoctoral positions and the need for several postdoctoral positions before a graduate were to get a permanent tenure track position, and increasingly in industry, a good position. Well, if you look at engineering, which is the lime green line there, there's been an increasing use, particularly since 2001, in postdoctoral positions. And that is something that I've been giving you more or less rosy views of the supply of engineers. I do find this postdoctoral phenomenon somewhat troubling. Okay, if you think about people going into engineering, one of the reasons more people might not go into engineering in school at any of these levels, undergraduate or above, is they don't see a rosy picture for engineers. And you've talked a bit about salaries, but actually real wages for engineering graduates have been more or less constant in the last 20 years. And if you look at this table, which I was able to get from a German colleague from National Science Foundation's data, it's got projections. These are by the Bureau of Labor Statistics of occupations from the growth in it from 2008 to 2018. The black is the growth in all occupations, and I think that's around 10%. If you look at engineers, that's just, I think it's 11.5%. So suppose you're thinking of going to school and you look at these projections, you really don't see from that picture a great increase in demand for what you would be getting an education in. Okay, so enough of the numbers. Okay, I want to turn to this issue of what do engineers do, what could be the competitive advantage of the U.S. in producing engineers. And what I wanted to show you first, again, comes from NSF figures. And this comes from 3 surveys that are administered to recent graduates as well as college graduates, I think up until 70 years old. So there's a cross-section here. And they're 2 different pictures of the relation of jobs and degrees, okay? On your left, essentially the purple or pinkish area is the number of individuals that in 2008 had their highest degree in science and engineering. So that's 12.6 million, okay? If you look at the blue circle, both on the left and the right, those are the number of individuals in what the National Science Foundation classifies as science and engineering occupations. They're 4.9. So what I want to point to is the intersection. Only about a third of the people with the highest degree in science and engineering are in science and engineering occupations. So on the right-hand side, it's just another look at the same thing, but I think a little more revealing. It's individuals with jobs needing a bachelor's level of technical skills in engineering, okay? There were 11.2 million of those. The green circle is the individuals with the highest degree in science and engineering who said in these surveys that they were in a job closely related to their field, okay? That's 7.9 million, and then the blue circle is, as I said, suppose you look at the intersection of those 3, okay? Of those requiring the skills, only 27% are in a science and engineering occupation, and 40% are in either the gray, the kind of lavender, and the blue. They're either not in a science and engineering job or their highest degree is not in science and engineering. They could have an undergraduate, but their higher degree would be in business or some other occupation. Okay, so to me that says that the National Academy of Engineering and a lot of other units in the 90s knew what they were talking about. there's a real need for engineers that can talk to other people. Actually, there's a real need for engineers who excel at the intersection of problems. And about 6 years ago, I was a co-author of a survey published by the National Academies of where multinational firms were putting their new R&D facilities. And essentially there are many things that came out very clearly in the survey, but one is I think virtually every graduate, if they're employed, is going to have to work on a cross-functional team, even if they're just working in a science and engineering occupation. And they're going to be globally distributed teams, okay? And that's really challenging. Something I don't have on the slides, in the early 90s, the National Academies published a small monograph that had the results of interviews with 17 chief technology officers of multinational companies. And they asked how the U.S. educational infrastructure did in terms of producing scientists and engineers. And they said we were absolutely fantastic at technical skills. We needed a little work on communication, and that most of the graduates, people in these companies, Hewlett-Packard, IBM, who came out, could not define a good problem for business, and that was a real problem. So one of the things that the university community at large has done, and this has been going on since the early 90s, is provide a number of programs that really broaden engineering education. And the real challenge here to me is you want to avoid ending up with engineers that are not technically superior. So you've got to broaden the education and not lose the rigor. And that's no mean trick, okay? There are a number of ways to do it. There are 4+1 programs, as I call it. The examples I have here are, I'd say they're random, but they're really just a function of ones I could immediately think of. Duke has a number of these. There are many minors in entrepreneurship because a lot of the employment of engineers has been in starting their own companies, particularly those engineers who invent something. There are increasingly joint degree programs at the graduate level. Stanford, for a long time, has had a JD, joint JD Master of Science degree in engineering. University of Pennsylvania is now launching one of these. Georgia Tech this year with Emory has not a JD degree, which allows you to be a practicing lawyer. It's a jurisprudence master's, and it's really to give you walking around knowledge of the law for bachelors. And when President Peterson, I was co-chair of the committee that started putting this thing together, and he said what he was interested in, because of the demographics of the job market, was that when people talked about a Georgia Tech grad, they didn't just think about somebody who, when they were 50, was a chief technology officer, of a company, but a CEO, and they thought these were the kinds of skills they'd need. And the best program on the map, another type of program is one that I created at Georgia Tech, did something similar at Purdue. And it's a graduate program, and in a nutshell, it teams PhDs and PhD candidates in science and engineering with MBA students and JD students over a 2-year program, and it's focused on the issues in commercializing fundamental research. And they're taken through core courses, but all of the projects are done in the context of the PhD students' thesis research. So it's really trying to, the reason that I came up with this program and its forerunner at Purdue was really this idea that goes back to these reports in the early 90s. How can you broaden the education of these people and not lose the rigor? And with that.
CTO perspective. Thank you. For the international perspective, you know about R&D and R&D facilities in other countries, and tell us a little bit about, from your perspective, the big multinational perspective?
Sure. You know, I'm very proud to be an engineer. And as Lance introduced us yesterday to the Big Bang Theory, those of you that know that show will appreciate Howard Wolowitz is my hero. He's the engineer on this show that the theoretical physicists berate constantly. And the reason I admire him is he actually makes something. And I think we need to draw a distinction between invention, and I totally agree with what Marie said, innovation. You know, we celebrate that act of discovery, and that's sort of the dream that people have. But invention is the start. Innovation is when you actually reduce that to practice and make something that's useful. So if you ask society who invented the light bulb or the car or the telephone, you'll hear Edison and Ford and Bell. Those men did not invent those devices that they're associated with. Edison was not the first to produce light from a filament, but he made it practical, made it cheap enough that we could enjoy it. And Ford wasn't the first to invent an automobile, but again, he made it practical. Same thing with Bell. So we have to understand that engineering has a unique place. We sometimes get lost, especially when we glamorize the invention part, and recognizing that society doesn't necessarily gain until it's reduced through a commercial enterprise typically to something that people can actually pay for. And pay for means they make a value judgment. So one of the things that differentiates engineering research, I think it's just as challenging as anything that we do, is that society puts the ultimate value on what we do. You know, the discovery of buckyballs was really phenomenal. The idea that there'd be a highly symmetric form of carbon that we hadn't discovered until recently and was actually ubiquitous. It was in soot and flames a lot of places, won the Nobel Prize. But the truth is, buckyballs really aren't good for much. You know, there's no commercial product. So you can get a Nobel Prize for science, but that doesn't mean society ultimately is going to get a benefit from it. So we've got to understand that distinction. And I think, you know, as much as we like to, we have a problem of everybody's trying to make their discovery relevant. So when the reporters come up to us, they ask, well, what's good? Why do you care about this? And people tend to go for the headlines and forget the bottom line. Understanding a good engineering science means you understand how to make something practical, how to make it affordable. And unfortunately, not everything that's possible is practical. And I think as an engineering community, we've got to do a better job of explaining the value that we create for society, and meaning that we actually make things that they can afford to buy, not things that we can make that are possible, but they're never going to be practical in terms of everyday life. So I think it's an important distinction. Finally, this talk about talent and globalization, I think, is also paramount. We have to recognize that an engineering training is a phenomenal talent base for a commercial enterprise or a government or university, obviously. But we sort of just have to look no further than our chairman. You know, if you look at Chad Holliday or Irwin Jacobs or Craig Barrett or Jack Welch, these were CEOs that were extremely successful, started out in engineering. And I've had the fortune to work for two great companies, General Electric and Dow, and what I've observed is that, just as we saw in Marine's charts, there's a leaky bucket here. A lot of engineering talent moves into other functions. Engineering is a great background for marketing, for manufacturing, for business leadership. In fact, if you were in the electronics industry, you don't show up at Samsung's door or IBM's door without being technical, even if you're a business leader, because if you don't understand the technology and the solid-state physics, they just don't want to talk to you. So unfortunately, the talent flow from engineering to these other disciplines is governed by a diode. It doesn't really flow back the other way. And there's a couple of reasons for that. One is just natural interest, but the second is if you stay out of engineering for too long, you're not technically competent anymore to come back. And it's tougher to compete with the people that have stayed in engineering. So when we talk about talent as a general perspective, we have to understand that not only do we have to look at the needs of the engineering that needs to get done, but the broader enterprise, especially if it's a commercial enterprise. And then finally, on globalization, I was lucky enough to build two labs. We built the first big GE lab that's in Bangalore, and then in Dow we built a big lab in Shanghai. And the idea that the United States has a monopoly on talent is just not true. Brains is globally distributed, and we have to maximize the assessment of talent across the globe. Now, there's two reasons that you go globally. One is application development. You can't send an English-speaking, jet-lagged engineer to China to solve a problem. It's just not going to happen. They need real-time people that can do the application development. But more broadly, you do want to have global talent assessed because you need a competitive advantage. Anybody who's in a leadership job has to understand that talent is the single most important thing that you do. Strategy is good, but talent is what allows you to execute, and there's nothing more important than talent. At least in my job, it was practically the only thing that will make a difference. And going to China or going to India allowed us to just broaden that pool. The thing that we seem to have forgotten is that while the United States is preeminent right now, there's no innate charter that says we have to remain that way. Especially in corporations, we sort of think in these kind of communities that research is a given. There's no charter or law or requirement that says a corporation has to do research. It's a privilege we earn by creating value for our customers, and the customers have to pay for it. So people may want a lot of things, but unless they'll pay for it, you go bankrupt. And so as we look at research, they've figured that out in Asia, and they are definitely trying to take what we have. And so we've got to be very jealous and guard the unique position we have right now, and talent is first and foremost. Thanks.
And that's going to be a lot of fodder for discussion. I hope you have questions. Dave Badgett is the entrepreneur on the panel, the software guy.
Right. I'm the guy who spends $1 million a year, not $1.4 trillion a year. So I'll tell you about how you think about talent when you have limited resources. I've had a hand in building 3 companies so far. 2 were sold, one to Sony, which was the game company, and the second one to Google, that was the travel search company. And the largest of these was ITA, and it was about 500 people when it was acquired. But from the standpoint of what we're talking about here, that's still really small. So at my new venture, which is called Inky, we're working on answering the question, why are you slogging through every single one of the mails in your inbox every day, figuring out which ones you should read? Can't a computer do that for you? We think the answer is yes. And so we're competing with companies like Apple and Google, Microsoft. You know, they have email systems. One of the things that's really funny to me is my niece is a country singer, and she's got a top 20 song now. And we have one thing in common. You'd think that engineers and country singers would have very little in common. We have one thing in common, which is when she tells people what she does, a very common response she gets is, "Oh, have you heard of Taylor Swift?" Yes, I have. And I get, "You know, Google has that email too, right?" I can't believe no one told me that. So why do I think that I can compete with my infinitesimal little resources? You know, with somebody like Google. Google has more people by an order of magnitude working on Gmail than I have in my entire company. There's a particular kind of engineering talent that companies like mine rely on. And good companies don't work like, good small companies don't work like good big companies do. For example, we don't have all the overhead. And to give you an example of that, we have one 1-hour meeting a week in the whole company. That's it. Every single other minute of our time is spent working on the product. But that's not enough. Actually, for us, talent is about magnifiers, about multipliers. And so there's this incredible phenomenon that's pretty well known among software people, which many of you probably haven't heard of, which is the 10x programmer. And this archetype, and it's the archetype that companies like Google and Facebook and Twitter are literally built around. This is someone who can write 10 times or even more, sometimes 50 times, as much working, documented, maintainable code as a good, solid, typical programmer at a large software company. So how is that even possible? It's interesting why it's possible. It's possible because, unlike in engineering disciplines where you have physical inputs, physical objects you have to fashion into other objects, in software it's all about ideas. It's about thought and data files, right? So these things don't have mass. They don't take up any space. And a single person can manipulate a conceptually vast object in this mental space just by typing on a keyboard. So if you think about it more concretely, imagine a single construction worker trying to make an entire skyscraper. It's just physically impossible. And yet a single person working on software can create an entire important product by him or herself. And this actually happens. And in fact, the big name software companies you've heard of, most of them had at least 1, 2, or a handful of these people in the beginning. And that's actually one of the reasons, if not the reason, why they are a big software company now. So I'll give you an example from my own past. ITA Software was worth $700 million to Google, so a lot of value was created there. And we had a whole business built around it, and it earned money, so it wasn't like it was a purchase based on an EBITDA multiple, so it was a real business. But at the core of that was a piece of software called QPX. And one guy, whose name is Carl DeMarkin, who's a good friend of mine, wrote about a third of that code himself. Now think about what that says. It's a 500-person company that built a $700 million valuation business around a piece of code. One person wrote a third of that. That's amazing. Here's the problem, though. There aren't too many of these 10X people out there. There are more than you'd think, but there aren't that many. And it's hard to motivate someone like that to come work for you. And here's the thing that I've found. I've actually had the privilege of hiring about half a dozen of these people in my career, and my formula is fourfold. Number one is have something really interesting and really hard to work on. Number two is give these 10X people a tremendous amount of freedom, but guide it towards some commercial goal. Protect them from bureaucracy and, for lack of a better word, idiots, because that's how they think about it. And number four, which you see manifested really directly in Silicon Valley, is cut them in on the upside. And so is there a lesson for the larger context here? You know, we're talking about trillions of dollars and millions of people. I think there is. I think 10X people are really creative, and identifying them is hard, partly because they know a lot about a lot. They might not actually have the highest SAT scores, but they're the most likely to have a mastery of both the foundations of modern cryptography and a working knowledge of cephalopods and their unique properties. So it's a combination of depth and breadth, and it's a little bit of quirkiness. And this is really what leads to innovation in my experience, and I think these people are the golden geese of our economy. One thing you have to understand about these 10X types, they completely violate all of the world's preconceived notions of engineers. They're more like artists. They have artist-type personalities, except that instead of spending their entire lives learning how to paint, they spent their entire lives learning technical stuff. And so you find them being hyper-creative, sometimes kind of fussy, usually pretty funny, but they're well-grounded in the basics of many fields. And they might have failed out of a class or two. But they can see these connections across disciplines that seem really bizarre to the rest of us. And these are the ones we need to attract and build our companies around. And it's not easy. And I think, from my experience building a 500-person organization, and over the course of time losing some of the ability to entertain and retain this talent, I've learned some valuable lessons. And one is that the 10Xer needs a space within the organization in which to run around freely and break stuff. It's really easy to overmanage 10Xers. You have to mostly leave them alone, but as I said before, guide them towards some commercial objective. You have to get them excited about something and get them to work with you in understanding how you can deliver it to millions of people. Because these are people who deliver value to millions of people. That's what they want to do. And a lot of times they have crazy ideas, and what you have to say to them is not, wow, that sounds really insane. That's never going to work. No one's ever going to buy that. You have to say things like, yes, I like the way you're thinking. Can we make this practical for 1 million people? And it really shouldn't be a news flash, and I think we all know this, but the 10Xers aren't all born in the United States. They come from everywhere, and I think most large companies are pretty good at accommodating differences, cultural differences. But we need to hang a big sign out on our front porch as the United States, I think. It needs to say we're open for business, we're hiring smart people, and we want people with creative and unusual backgrounds, because 10Xers are always like that. They don't always attend Ivy League schools, they don't always grow up in affluent households, and some of them seem kind of weird. So the skill we need to identify, I think, a key skill, and it's critical, it's not just a key skill for someone like me, who can spend $1 million a year building a business, who has a startup, it's an absolutely essential skill. But it's a key skill for every business, is to be able to figure out how to identify who these people are. And so, for example, I don't really care if this 19-year-old Sri Lankan girl who's been selling iPad games since she was 15 got a bad grade in chemistry. because she's already showing signs of being a possible 10Xer. Now, she probably isn't, but she's certainly showing signs that she might be. She's the one I want to talk to. And I don't care if she got a 4.0 GPA, because nobody gets a 4.0 GPA by taking risks, and all these 10X types are risk takers intellectually. And I think it's really important for us. There's a lot of dogma in engineering, and that's a good thing, because when you build avionics systems, for example, you want them to work. But we need to also keep an open mind when we're confronted with strange ideas from otherwise accomplished and brilliant people. Think about the miracle year of 1905 in science. What became this now utterly empirically validated, absolutely established theory of relativity seemed at best controversial and at worst crazy. So time slows down when you go faster because the speed of light and not time is absolute? What? It's crazy, right? Even Einstein himself felt the need to fudge by adding this magical cosmological constant, because if he didn't have it in there, it showed somehow that the universe was expanding, which was crazy. Unfortunately, he was wrong. Actually, it seems like it probably is expanding. He didn't need his constant. So when you think about the future of the nation and the economy, I mean, it's really important to think about the large aggregate numbers and how to get more people through our pipeline globally, get more of them to come to America. But it's also important to think about that handful of 10X people, because they're the core of these small companies that become the great companies. Thanks.
Excellent.